the award lecture and also our second keynote at the same time. So I don't want to say too much about Thomas because he's going to be introduced by Roberto De Marca, the IEEE president-elect, after his lecture when he actually gets this award. So I don't want to bore you too much. However, one interesting story is that Thomas has been the program chair of Hot Interconnects number 3. So that's 18 years ago. So, and he still has a shirt which he's not wearing today. So, okay, so yeah, welcome Tom and his lecture.
Sure, thanks. Okay, here we go. Okay, so thanks very much. It's a pleasure actually being back here. I'm going to do a little bit of history about Hot Interconnects in a little bit, which actually motivates to some degree some of the work that we've done. What I'm going to try to do though is there's a bunch of deep technical material that's going to be a little bit unfamiliar to this audience, so that's going to take. I'm going to educate you about BGP. I've been spending about the last 15 years of my life trying to fix BGP, and partly that's so that you don't have to. But I'm going to give you kind of the couple-minute version of my talk, and then I'll dive into more detail as I go along with it. So here's the elevator pitch. So the internet has issues. It's had issues for a really long time. So if you really wanted to build a very highly reliable system, so one that you could really depend on for things that really mattered, not the Netflix of the worlds, but just, if we're going to use the internet as the telecommunications facility for commerce or for medicine or for the military or for whatever else you might want, the possibilities and vulnerabilities of the internet are well understood by people who work in the area. And they're very frustrating in many ways. These are things that we understand and have understood for many years, almost decades in many cases, and that actually now we mostly understand how to fix. And so a positive of the research community's efforts over the last 15 years or so has been to develop a set of solutions for pretty much any problem that's known in the internet. What we haven't had is a lot of progress at actually getting those changes into practice. You could look at pathological routes, you could look at route convergence issues, you could look at misconfigurations that cause black holes or brownouts, denial of service issues, basically across the whole spectrum of things that would make you worried if you were going to if you're going to rely on the broader public internet for something that really, really mattered, that these things should be keeping you up at night. So, and the principal problem for all of those problems, and the reason why they're difficult is that it's a local problem causes a global outage. That is, that there's not local effect for local errors. So if someone misconfigures a router in an ISP in some portion of the network, it can affect people for whom there's no direct commercial relationship. So an ISP advertises a short route to somewhere that then starts attracting traffic that it never carried before it made that error. A similar problem would be if somebody changes a route in some portion of the network, that destabilizes things that can cause convergence issues that ripple out across the network that can affect a large number of organizations and participants that really don't even have any direct relationship. So in this case, you have this flaky ISP in the middle. Power Data is trying to talk to Amazon. If it happens to be the case that Sprint uses flaky ISP for getting its traffic to Amazon, even if Amazon wouldn't choose to use flaky ISP, and even if Power Data, the person who's sending the data, wouldn't choose to use it, so Comcast wouldn't choose to use this flaky ISP, because some decision is made in the middle of the network to use it, then the people who are at the endpoints don't really have any choice in the matter and are kind of stuck with the difficulty. So the elevator pitch then is really to think about a different model for how we might go about implementing a wide area internet service, and the model is really by analogy. So today I can go and buy compute cycles, I can buy storage cycles from data centers, and that's a very active and very productive thing for enterprises to go do. but I can't do that for internet traffic. And so what if I could? What if I could go ask a remote ISP to give me transit? And what I mean by transit is that some ISP I'm not a direct customer of, if I can get you packets, if I can get packets to you, which, yeah, the internet's connected most of the time, if I can get packets to you, you will carry those packets across your network from one POP to another, and then exit it at some place elsewhere. And I'm going to argue, and it's going to take me a little while to get there, that this is going to allow me to get much better security and reliability than the current model that we have, which is basically the model that we have today is your local ISP promises you a service that it actually can't deliver for you. That is, it promises you the ability to deliver IP packets anywhere in the world, except it only has a local network that it only controls some portion of that. So the decomposition here is what Amazon promises you when it sells you cycles at EC2 is it has the cycles at EC2 to sell you. It's not promising you something that it doesn't actually own. But the internet's protocols are designed in a different way. And what that's going to allow me to do is to actually change this local problem from a global problem back to a local problem. That is one that I can avoid. Okay, so the broad picture of this is, the research agenda of the networking of the protocol networking community. That's a little bit different from the people in this room. The protocol network community is mostly that you get to ignore them. I mean, that's what they'd like. The protocols work, and you don't have to think about them. They just work and they do what you want. So a good network is one that I don't have to think about. When just to give you a little bit of history, I actually graduated from college with my dissertation right around the time that Hot Interconnects started, so about 20 years ago. And one of the first projects I started on was this one, which we published in '94. So I don't know that I'm actually been coming to Hot Interconnects longer than, I guess, Dan Pitt. About the same amount of time. So, and this, we wanted to make a couple different cases here. And in some ways, this is going to seem like it's a story that is going to seem very obvious. But at the time, it wasn't. So the first of these that we wanted to make an argument for was that scalable services should be built out of commodity components. And I can point out that this is not something that 20 years ago, we actually thought that there was a common view of the research community. If you look at how Alta Vista, which was the first internet search engine, built basically at the same time, they built them on the largest scale DEC machines at the time. And you might think DEC is no longer around, and for some reason. But the idea was that if you're going to build scalable services, you were going to bend iron, try to put as much computing power inside of the box as possible, and that would give you the better performance. And what we saw, and I think what the Hot Interconnects community saw, was the opportunity that fast networks and fast switch networks were going to give the ability to kind of rethink how data centers would work. And that this would motivate a whole sequence of new distributed systems design. That story essentially immediately became widespread. So by even just a few years after that, this was how every scalable web service was being built. At the same time, we actually made a second, and this is, mea culpa to some extent, a second prediction or a second observation, which was that low latency, low overhead message passing was really essential for building these types of applications. That turned out to not be quite so true. That is, we've gotten a long way without having as really very, very low latency, low overhead message passing. But you can see today that we're about at the cusp of being able to do the types of things that we were envisioning 20 years ago. So to some extent, it's taken a very long time for some of these ideas to get into practice. So it is the case that the research community sometimes, hits the button and the technology transfer happens instantly, and sometimes it can take a long time. And I don't mean to say that one of these is good and one of them's bad, but you can kind of see that the research community actually has this model in its head that you may sometimes take a long time to have things happen in practice, and that question, right? Is it the case that we understand now how to fix the internet, and therefore we should just wait a little while until the market hits the right place and it really becomes important for it to happen, or do we have to kind of push harder at it? My dissertation research, I just recently heard, got implemented into Windows. which is, hey, yay, except I wrote it 20 years ago, so, right? So for those of you who are students, just have a little bit of patience, I think is what that would be for. Okay, so flash forward a few years, and actually, this is essentially the motivating factor for me getting into network protocol research was this graph. So we started measuring, we wanted to build essentially we were interested in building a dynamic data center, so one that would shift load across multiple data centers. And what we found was all the algorithms we ran didn't work, and they didn't work because the internet behaved badly. And well, we could have programmed around it, but actually we thought that the fact that the internet behaved badly was kind of interesting. And which is to say that if you took the shortest distance between 2 points, which you would think of as being a direct line, that is sending packets from A to B, often that was much, much higher than going indirectly through some other places. That is, that the triangle inequality doesn't hold for the internet, that sometimes you have pathological routes. In this case, traffic between Walnut Creek and Los Altos actually was routed through Philadelphia for whatever reason. And okay, so now, the amount of this was astounding. You think, okay, one of these cases would be okay, but this would be something that you would find a lot. So about 40% of all routes in the internet at the time were worse than an indirect route. That is, you could find nodes in the internet that would get better performance if you went through them than if you went directly, which is a pretty poor, wow, right? And about 10% were pathological. That is, they were wildly off base, like this one, for example. I mean, that's a pathologically bad route, not just a little bit worse than going indirectly, but just a lot worse than indirectly. Okay, so we had this question. If you go back and look at the paper in Hot Interconnects 98, you could see us posing this question, which is, okay, what should we do about that? What's the lesson that we should take from this? So one would be, we could fix this. That is, we could just put a node at each of these places that has better performance and then redirect the traffic, and then the end user would be happier. And we thought about that for a little bit and thought, oh, okay, that can't be how you would do things. But maybe if we just tell people about this, then the ISPs will become embarrassed enough to fix them. So what's the current world look like? It's gotten worse. Fast forward 15 years, and instead of 40% of paths being worse, it's like 60% of paths being worse. Instead of 10% being pathological, more like 20% being pathological. And we actually have commercial Detour routing services. You can buy Detour routing services from Akamai and a few other companies. I got embroiled in a patent lawsuit on this topic a while back. Okay, so that's pathological routing. But what about outages? So one of the things we wanted to ask was, okay, does it also apply for outages? So how often is it the case that you can communicate from point A to point B if you want to over the internet? And how much trouble, how often do those things go out? And so what we did was we looked at who would be the most connected organizations in the existing internet. And they would be data centers. They have a huge incentive to be able to get connectivity to everybody, because that's what their business is giving you access, giving the services that run inside of a data center access to everyone. So we took a data center at Amazon and measured over a couple months how many separate instances were there outages to portions of the network, portions of the internet. And we found 2 million of them. And this is a probability distribution graph. So it's how often it is that you see a certain outage based on how long the outage happens. So the hump there is short-term delays. So that is, they're essentially route convergence issues. So what BGP does to you. So even if you have a physical connectivity between two places, you may not be able to get even if you have a physical link or a sequence of wires that are all working, all the routers in the meantime are working, all the ISPs in the meantime are working, it still will be the case that you might not be able to get traffic through. And the reason you might not get traffic through is just that the route tables are still in flux and that they can take some time to get back together again. And I'll give you some examples for why that's the case in a little bit. Anyway, so almost all the outages are of that flavor, that they resolve after a little while, but in the meantime, you're not able to communicate. something like, I don't know, 30% of the packet loss on the internet, on the global internet, is due to these route convergence issues. That is, somebody changes something about a route, and then that causes routing consistency that then takes some amount of time to propagate. In the meantime, you're dropping a lot of packets and losing them. As I think Amin mentioned this morning, the actual ISPs internally almost never drop packets. Like, we actually understand how to build networks that don't drop packets. That's not the problem here. And then some portion of these are actually long-term, and those long-term ones, usually a human has to get in the loop for fixing them, and that they actually represent almost as much downtime as the shorter ones do. And now you might think outages, that's fine. If you're just downloading from YouTube or looking at Netflix, then an outage it's not that big a deal. However, this is where we're going, and that's where we're going, right? Which is, people are now using the internet in order to do health monitoring. In fact, there was this amazing email exchange that happened when Amazon's data centers went down a couple years ago, which is somebody posted, I was using Amazon to do health monitoring of these people at home, and now it's offline, and what am I supposed to do? Anyway, so yeah, well, they didn't, it's just monitoring, so hopefully they lived until the system came back up. Okay, so if we're going to be in this world where we really want to depend on the internet, then what can we do instead? And I'm going to try to walk through where are all those problems coming from, and why are they so difficult to fix, and why can't we just go and fix them? And if out of this is you happen to be somebody who could go and make this happen, then I'm fine if the fix is let's go apply all the things that we understand now about how BGP can fix. That would be fine too. But at least now I think actually we have two different paths, and maybe we can compete against them. I'm going to go through a little bit about how internet routing works. For those of you who know this, it'll be boring. For those who don't, then it'll be almost incomprehensible. And then a catalog of I realize I have been studying this for 15 years, so it's not an easy set of things. Okay, so the internet's a this is going to be obvious, right? The internet's a federation of autonomous networks, which is that one of the key aspects about any scalable system. And then the internet was claimed to be a scalable system, designed to be a scalable system. That is, ability to go work at global scale. And it's obvious that any network that's going to work at global scale has to involve multiple organizations. And so the key thing that you're going to have to solve is what's the coordination function between those different organizations. And the way that the internet works is that what we're going to do in order to get a route is to advertise from wherever the destination is, backwards towards the client's computer. We essentially propagate information back. So this is, I guess somebody doesn't have the right font. But that was something. Anyway, so we're going to propagate this back. Now you can see it's, there was an arrow there, but it's okay. We're going to propagate this, so the web server ISP will say, if you want to get to the web server, this is how you get to it. L3 will say, okay, if you want to get here, then you go through me in order to get to the web server. AT&T can say, okay, if you want to get there, then you go through me, going through L3, going to the web server, and so forth. And eventually UW finds out that it's there, and will, again, my apologies for the font, will arrive back at the destination. So in the other direction, then the traffic flows. So the route advertisements flow upstream, the data flows downstream. Now, if I want to go, because any path, in order to be able to get communication to happen, you need both directions to go. So you're going to also do this in the other direction. That is, UW will need to propagate how people get to it, and then they will propagate out, and then the traffic will flow in a different direction. This causes asymmetric routing. So that the policy is decided. In this case, the policy is decided on the forward direction. How the traffic goes in the forward direction is being decided by AT&T as to whether it's going to go to Sprint or L3. And on the backward direction, it's being decided by L3 as to whether it's going to go to AT&T or Sprint. And that those independent decisions can be made independently and are made opaquely and are made without regard or knowledge or control of the endpoints. So those are all decided internally in the network and done without without anything, and usually they're based on dollars. That is, who's going to pay somebody more, or as opposed to performance or other issues like that. Okay, so allowing these policy-based decisions is fundamental, and then also much of the cause of the problem. Okay, so from how to get a router level data from this, well, you go through some set of one ISP will then potentially peer in multiple places with another ISP, and then we'll just pick one of those places in order to get the data to the destination. And but the equivalent route from an AS level might look completely differently than that. And then the actual end-up performance and availability goes. So this is an example of a path. This is the type of thing, if you go and measure the internet, you'll find easily. That is, it's not difficult to go find them. And so we've actually been building tools to be able to go try to diagnose these types of problems. So in this case, we were just measuring different parts of the internet against each other. And we found this round trip, this happens to be between Orlando and Seattle, and I live in Seattle, but it could have been between, Budapest and Frankfurt. It could have been between any two places on the planet. And this is very common. I mean, if you run a data center, you see these types of events a lot, which is poor performance to some set of customers that you have. Why is it that their traffic is going through some circuitous route? What's going on? Well, one thing that you can do in this case is to issue a trace route. So in this case, if you're seeing it from Orlando to Seattle, you could issue a trace route from Orlando. I think this is from Orlando to Seattle, and which is to say, it will tell you all the hops between you and Seattle. And in this case, it's going from Jacksonville, I think, or Orlando to Jacksonville and so forth, up to Virginia. Then for some reason, some policy decision that's being made, that it comes back down to Miami, and only after that does it actually get off to Seattle. And you're like, oh, okay, that's bad. Now you could ask, what can I do about it? If you're the person who's in Orlando trying to fix this, what can you do about it? Well, the decision's being made in Virginia, and you probably by some ISP you have no direct relationship with. So it's actually quite difficult for you to go fix it. But at least now you know who to blame, like somebody on this path. But however, your round trip performance is both sides, right? And one of the questions is actually in the existing internet up to a couple of years ago, you had no way of knowing what the back path was. Like if you had a friend in Seattle who could send you packets, then you could know. But otherwise, you had no way of knowing. So we built this nice tool called Reverse Traceroute, which if any of you are trying to diagnose paths is really helpful, and it's online and whatever, which will actually tell you the back paths. So I'll just show it to you. I'm not going to show you how the tool works. It's magic. But it'll show you what the back path is just for this example. And this is not an odd type of thing, which in this case, the traffic goes to LA, and then oddly enough, comes back to Seattle, and then through Chicago, and then off to Jacksonville. And this stuff happens all the time. And it's why? Well, somebody decided that there was at some point most likely that there was some point where there was overload in some portion of the network, and they installed a policy which was to send traffic in a certain direction in order to avoid the overload. And then somebody forgot about the policy, and it just sat there for a long time. As you might imagine, right? These things are operationally pretty difficult to deal with. And as I said, basically, what do you do then? Well, okay, I can give you this information. I can tell you exactly what's going on, but that's a different thing than saying you can go fix it. And as we say, even though we've known about a lot of these problems for a long time, we haven't really fixed it. It isn't necessarily so clear that there's somebody at the other end of the email. So here's another example. So we had done some work on understanding where these route convergence problems happen. So as I said, the Border Gateway Protocol, so that's BGP, is an opaque policy routing mechanism. The idea is designed to give ISPs the ability to control everything about how their own network works and not tell any of their peers what they're doing. So they can decide for any traffic that's coming in what they want to do with it. That is, do I send it to Sprint? Do I send it to L3? Do I send it to somebody else? And what I need to be able to do is to advertise that I am willing to traverse the traffic to a certain destination. But what my policy for when I decide to do that or not is something that's under my control, and I can change it unilaterally. And the mechanism for this is that the ISPs, or in this case the slide says ASs, but you can think of this AS and ISP being synonyms in this case. The ISPs send their most preferred path to the neighboring ISPs, and then they propagate that. If they decide to use the path, then they add themselves to the path and then go forward. Now the algorithm for doing it is that you start using it right away, but you don't propagate the change until there's a delay. And the reason for that, it turns out, is that otherwise you get that the algorithm is actually one that can lead to exponential explosion in number of messages and amount of overhead. That is, as an algorithmic level, the protocol is actually kind of weak. But eventually the path will propagate to everyone. So here's an example, which is basically just a pretty simple example to show how failures cause outages, temporary outages within the internet. So in this case, I have an ISP5, and it has a bunch of neighbors, and some of whom have to go through some other neighbors to get there. ISP4 has a policy that says if I want to get to 5, use 5. And that's a pretty obvious one. 1 similarly says if I want to get to 5, you should use 5. But if this link is down, then you should use this other way through 2, 4, 5. And then similarly 3 says, oh, okay, my preferred way of getting there, I have a bunch of different ways that I can get there, but my preferred way of getting to 5 is to go through 4. But my second preference, if that doesn't work, is to go through 2 and then through 4. And then similarly, you can think 2 also has this preference. It wants to go through 3 and then 4 if it can't get there directly. OK, so what happens when there's a failure? Well, OK, so I'm going to apply the change, and then I'm going to wait a little while before I propagate it. So 4 says, oh, OK, I can't get to 5. Great, I'm going to change what I'm doing now. I can't get there. OK, fine. I need to learn more stuff in order to know. But it's going to then propagate the change to its neighbors. Those neighbors will then immediately apply the change, start using their second best route, and propagate the information about that second best route to their neighbors after a delay. So essentially, instantly after they find out about the failure, they're each going to start sending traffic to each other. And while that's going on, like you would think, okay, like not too long, but essentially there's a delay built in. During that period of time when they're figuring it out, there's an outage. If either of these try to actually send to 5, they're not going to be able to send. That is, it's not going to get there at all. Okay, so how does this work in practice? If you go and simulate, take the measured AS path between all peers within the internet. Actually, the internet is not that large anymore. There's only about 3,000 transit ASs and transit ISPs on the planet. That is not a very large number. And you can go and measure all of their interconnect. That's not so hard. And then what we did was we simulated what would happen under standard policies if you started simulating failures, right? What would happen if an ISP connection disappeared? And what you see is, and then had the BGP algorithm working, is that in a lot of cases what will happen is that you will get an outage. That is this is a cumulative distribution graph in this case. So it's the fraction of ISPs that get disconnected by a certain failure. Over here, it would say, in 40% of the time, you will actually disconnect something like 20% of the ASs. So in some sense, it's more likely than not when you have a failure that you're going to disconnect some portion of the internet, at least temporarily, and then they'll propagate their updates and so forth, and eventually they'll come back together again. Policy changes also cause it. So this is one of the reasons why the internet doesn't get optimized, is that anytime you change any of the policies that would mean you should optimize it better, those also cause outages. So people who are on the operations side, should we optimize this if there's going to be this several minute outage for our customers if we do so? The answer is no, unless it's really important, then they won't go about it. I won't go through the example, but it'll do this. And actually, it turns out for policy changes, they're even worse, have worse effects in terms of reliability than other ones. So you can fix this. I will not bore you with the details. But you can fix it at this protocol level. And you might imagine how you would go about it. Like if you think about it in the right way. You could think about fixing each of those individual problems. But one of the ways that you could think about it would be that if inter-domain routes switch synchronously as opposed to asynchronously. So if instead of thinking that what we do is we make some local decision and then we propagate the information to somebody else and then we make another local decision and then we propagate the information. Rather, if we say, okay, actually what we want is global connectivity, and it's only useful if we have global connectivity, maybe what we should do is apply the changes together. And then we only have the problem of, well, what do we do in the meantime while we're figuring out what the appropriate next state of the world is. And it turns out that if all you do in the meantime is route your traffic through a tunnel to a tier 1 and then ask them to get your traffic to the destination, that's good enough. And that'll mask almost all of the failures that you have. So as a protocol, that's actually not so bad, but there's, the likelihood of that actually happening is pretty small. It would require global agreement, changes to every router on the planet, and I should point out that inside of ISPs, where you actually have the ability to have one organization decide everything, inside ISPs had a delayed convergence problem about 20 years ago, and they fixed it. Like ISPs themselves don't have this problem internally. It's only when they're communicating with each other that there's an issue. So another issue that you can find is that there are these outages that last a long time. So convergence issues was that hump in the outage curve. But also there's these long tail of outages that can last hours or days. And what's interesting about those outages is the vast majority of them are avoidable. That is, you might think, oh, well, if there's an outage because there's a failure and there's no connectivity, then there's no connectivity. But actually, usually, it's the case that there's connectivity. Either there's detour connectivity, that is, you can get there through somebody else, or there's asymmetric connectivity. That is, I can get there in one direction, but I can't get back, which implies that there's actually physical connectivity, but you're not using it. So this is a pretty common situation in how people diagnose problems in the internet today, in the wide area internet, that is the public internet. Which is, you'll have some problem, you'll observe it, somebody will say, I'm trying to get to through level 3, but it seems to get into a black hole in DC, and does anybody know what the problem is? And they'll actually mail this. I mean, like literally email this on a message board. And then somebody else will say, oh, okay, I'll try it. And they'll say, I get lost in Denver. This is literally from the message board, right? So is this the same problem? Is it not the same problem? It's like, how do you know? And actually, they ended up just giving up. Like, eventually it was fixed. I mean, presumably somebody at level 3 or some other network might actually not have been level 3 at all. Somebody figured out what the problem was and then fixed it. Maybe didn't have anything to do with these people, but these people were out of luck during all of the period when this was happening. I think it was several hours later that they fixed it. So these long-lasting outages are repaired only because somebody fixes them. They're caused because the internet has this difference between the advertised routes, that is the control plane, is not necessarily reflective of the data plane. So somebody could advertise a route and then not deliver traffic on the route, and then if the route gets used, then you have a black hole. And you have an avoidable black hole because if only I didn't advertise the route, then we're done. So examples that we've seen are corrupt. Generally they're just chasing down these individual cases, right? Corrupted memory line cards, bad cross-layer interactions. A really common one is you have a misconfigured backup route, which you don't notice because you never use it, except when there's a failure, in which case then you have a black hole. So these all basically come down to the notion that the control plane doesn't need to match the data plane, and they're complicated by this lack of visibility. So we've been building tools, which I'm going to skip through this so that I can get to the punchline here. But they're tools for being able to diagnose failures. And actually, if you are in the business of trying to figure out where problems are, then you should come see me. But I'll just this animation will take a little while. Basically, what you would think of is once you have the ability to probe everything and to be able to understand what the paths are going forward and backward, and also to be able to spoof packets, so ask somebody to send a packet for you, then that's enough to be able to figure out whether there's a problem. So for example, in this case, I have the VP, a vantage point somewhere in the network, given that the source can't tell where the problem is, maybe the vantage point can see whether different nodes are up, and therefore it can give it some extra information. So in this case, the target is up, therefore the problem has to be on the path. But we don't necessarily know where the problem is on the forward or the reverse direction. So we start pinging people in both directions, and then actually one thing that we can do is to forward the traffic from the source to the target and then off to a vantage point, and then that can tell us the forward direction is working, and so we can start looking at the backward direction and so forth, and then essentially do the same thing in the other direction. And in this case, I think the error was actually in Rostelecom rather than where you actually thought it was on the forward direction. But, sorry, this is going to seem like I'm beating a dead horse here. What do you do then? Well, okay, Rostelecom is messing up your traffic between these two places that didn't actually think that they were, either one was actually part of the Rostelecom network. So usually it's in a remote ISP with no direct commercial relationship, and you actually need somebody to go intervene. We actually came up with a way of fixing this at protocol level. What you really want is the ability to tell the network that they should avoid using Rostelecom. That is, to tell all of the neighbors of someone that they should stop routing through this node that's actually dropping their packets. And if you added that, it's trivial to, it would be trivial to add, but it would also require everybody to adopt the change and go forward from there. And that's going to take a little while. And you might think, okay, I really must be overstressing how difficult it is to get things done in the internet. I'll just take the simple example of prefix hijacking as your canonical thing of how long it can take. So prefix hijacking is a problem that's been known. This is work that we didn't do at all. Has been known for over 15 years. And the idea is there's no authentication in the internet for someone to say that they're the origin of traffic. So if I say that I'm willing to source traffic for or receive traffic for deliver traffic for a particular prefix or for a particular IP address, I just advertise it in the network, and the network accepts it, and then I start getting traffic. And this is kind of a known problem because what can happen is somebody maliciously injects things, but much, much more common is the accidental misconfiguration. And there's a great story along these lines. Cisco used to get a lot of their prefixes hijacked, and it just happened repeatedly. And the reason was that they had built this manual for programming Cisco routers that had a set of instructions that were how Cisco sets up their routers, and people would cut and paste and unfortunately use Cisco's prefix in the instructions. And so they would paste it, and then there would be this router that would think it was Cisco and would advertise Cisco's prefix and then hijack. So again, this is something that you think, okay, I could fix it. And there's been a sequence. I mean, there's an active IETF policy. I very much sympathize with the person from Facebook who said, you know, that whole standardization thing is really overrated. Very little benefit unless everybody adopts, and it's very difficult to get everybody to adopt. Route hijacking is essentially the same problem. That is, somebody can, even if they're not originating the data, originating a route, can essentially hijack it by advertising a shorter route. This happens, both of these things happen regularly on a small scale, and sometimes large enough for the New York Times to start reporting on. It's a well-known problem with well-known solutions, and it's a vulnerability. Again, if you were going to start depending on the internet for something that really, really mattered, which we are starting to do, then that's a problem. And us, again, I start, doing this for basically everything here. But route control would be another thing that you would actually want out of the internet if you really wanted to depend on it. So the DoD had its traffic hijacked to China recently, which you would think of as not being so good. So you would like the endpoint to be able to say that, these countries aren't where my traffic should go. And again, that's not technically difficult. I've actually done a bunch of work in distributed denial of service. It's a similar problem. We actually understand a lot about how to fix distributed denial of service. Very little progress in practice. You can buy denial of service protection from Akamai and a few other companies. Largely, it's for static content rather than dynamic content. And woe behold if you actually get on the bad side of Anonymous or other cyber terror organizations. So the internet has issues. Okay, so how are we going to fix them? So one is we could take our known solutions to these problems, package them all up, try to get them through the IETF, and then say, look, this is what we need for a modern telecommunications facility. That's what we need. And then wait 20 years. So the underlying problem is that, and I'm going to argue this is really the underlying problem. The underlying problem is the ISPs offer a service which they can't deliver on. They're offering you a service that is packet delivery service to anywhere on the planet, but what they own is a set of resources that are local. And as a consequence, that thing that they're offering you when they offer you packet delivery service is something that depends on the trustworthiness of the rest of the internet, of other organizations. Actually, in many cases, competitive organizations are the one that you have. And you actually see people doing malicious things between different ISPs as well. So the idea behind this network as a service idea is, could we construct an interdomain network, where ISPs only have to promise what they can deliver themselves? Because we actually find, right, we know that the ISPs are great at when they can control their own networks. So this says, look, let's have network operators offer the services they actually provide. So, which is that what an ISP actually does is deliver packets that arrive at one part of their network to another part of their network. That's what they do. Okay, we bundle it with all this other protocol stuff, but that's what they do. So could we then make that the thing that we ask of them? So could they sell the task of getting traffic from, enter at this pop, exit at that pop? Okay, I have to add a few extra things. Okay, I want to be able to swizzle the packets because, we understand from OpenFlow and other kind of packet management systems that we have a lot more flexibility. If the packet that arrives, I need to be able to modify slightly as it goes through the network, which is to say, okay, if it arrives on this address, I'd like to be able to change the address so it exits with a different destination address. That's going to allow me to do things that I wouldn't do otherwise. And then I might be able to add added value services. In all of these cases, it's the ISP selling the service, right? So it's not that I'm not forcing it to do it. It's only optional. If they'd like to be able to make some more money on selling me a service that will traverse their network, then I could go forward. So what does the enterprise do with this if they had it? Well, if I had it from everybody, then I could stitch end-to-end paths, right? And I could know exactly where my traffic was going to go, and I'd be paying everybody for whatever they were doing for my traffic. And if I was willing to pay more for more direct routes or less for other direct routes, then that would be fine. And I could provide any embedded services that I wanted in the middle there. And they would be based on advertisements that the ISPs would have. In just the same way that if I wanted to build a global service, I would buy, like if I wanted to build Facebook without running any data centers, I could go buy data or Twitter, say. And then I could go buy rack space, or I could buy compute cycles from any number of data centers around the planet and then just use them for building my service. And the same way here, I could build out these end-to-end paths from getting resources from others. And then one thing that I'll show in a second is that portions of paths may use the plain old internet. And of course, you need some kind of authentication inside the packet to prevent hijacking. So why here? That would be the other way of putting it. Why now and why here? So everything that this community is doing in terms of building very fast and very efficient packet processing, which has now become standard, like what the ISPs are doing internally, is an amazing amount of packet processing on every packet that traverses the network. And it's because, hey, I need to manage it. I compress it if it's on cellular. I need to do IDS, deep packet inspection, and so forth. We've gotten really, really good at doing very fast packet management. And Tylera has an example here, but this is just the data here is for essentially what a state-of-the-art Intel machine would give you per core will keep a 10 gigabit link busy. And what that means is that you can do a lot. And so this is for very minimal packet processing, so just doing the IP packet processing. So that potentially you can do a lot, you can actually handle at internet scale every packet. In fact, actually in software, we're probably processing every packet that traverses the global internet already. So why don't we take advantage of that? So distributed topology updates. One of the reasons, actually, Amin had mentioned this in the morning session, which is the internet and actually networking protocols traditionally have been designed with this notion that it was important to do localized intelligence. That is, that we needed to be able to decide locally at the place where we detect the failure to be able to do local topology updates and local information that's going to recover from whatever the failure is. And I definitely like it as a protocol. I mean, as like a protocol designer, that's such a great problem. However, do we really need it anymore? Well, our networks are very, very fat. Saving topology updates, thinking that we can't propagate information about topology updates everywhere that needs to know it, that's probably no longer an engineering need. I mean, it's something we still do. We still try to make local decisions locally, but it's not so clear that we need to do that anymore. So do we really need to be able to do localized topology management? That's not so clear. And then ISPs have made just an immense amount of progress. If you look inside the ISP, I've mentioned this before, but roughly a couple orders of magnitude more reliable inside of an ISP versus traffic that crosses an ISP boundary. So can we depend on it? So here would be a kind of a scenario to kind of take you off, to kind of give you something to think about. So if you're a large-scale telecom, which is like, who would be the user of this? So if you're a large-scale telecom, you have a lot of packet processing. Basically, okay, you're doing compression, you're doing packet shaping, you're doing IDS, you're doing a lot of things for these smartphones that are on the other end. But people measure you on how good your performance is and how effective your performance is. Nevertheless, 70% of your traffic leaves your network. So 70% of your traffic is not something that you're keeping locally or thereabouts. So for 70% of those packets that are leaving, it's like, oh, okay, I don't have any control over these anymore. And so now how good I am at using the over broader network to be able to get that traffic to where it's supposed to go, then that's what my customers are going to think. So there's a well-developed market for premium service, but no real way of actually having the telecoms be able to manage or do anything for this 70% of the traffic that leaves their network. So potentially this would give you the ability to manage your traffic beyond your boundary. There are a few design principles which I'll skip by quickly so we can get to questions. But one of them is just how would you go about building agile and reliable ISPs, and then how would you give incentives for adoption. So the basic model would be software processing at the edge of the ISP, and then routers at the core, hardware routers at the core. And is that plausible to do? Well, software packet processing has made a huge number of leaps forward over time. So the total internet traffic, more or less, roughly, again, this is an estimate, not a measurement, roughly 100 terabits. And if you kind of do the math, well, okay, 10,000 cores or thereabouts would process every packet in the global internet. So in order for me to be able to do this type of thing is much less than what we already assume that Google or Facebook or whatever is already put in place, or even these companies. Actually, if you go and ask under telecom companies how many middle boxes they're running, so how many separate devices are they running in their networks that are doing software packet processing, and the answer is many, many more than, like an order of magnitude more than this. Just on their own traffic. And then for that, you need a software layer. And so let me just point out this the incremental adoption just to kind of wrap it up. So how is it that if I end up needing to get resources from the various elements that I'm interested in, how does that give me something that's incrementally adoptable? And the idea is going to be that you don't need to have everybody adopt in order for this to be useful. So if AT&T gives me an address that I can send to with an authenticator over the real internet, then even if I have a flaky ISP, which somebody is going to use instead, then possibly that'll give me a way of exiting. So even if Sprint is using this flaky ISP and would otherwise direct my traffic, Sprint is not going to use the flaky ISP to get to AT&T. So if I can just get to AT&T and then ask AT&T to send off to Amazon, then I'm done. So I can actually eliminate a bunch of the problems that I had talked about just by shortening the path lengths. And so from the incremental perspective, it says only a few people need to adopt to be able to get around a bunch of the problems that we have with BGP. Because if only BGP were path lengths of 2 or 3, then it would be much easier to manage. Because basically the ability to have convergence problems and the ability to have prefix hijacking and route hijacking would be much, much less if we had shorter paths. So shorter number of ASs. So here's a concrete example of it. So if you look at at the total AS path again, and asked what the fraction of sources that will get polluted using BGP if I inject a prefix hijack. Well, you'll have some distribution there. I guess roughly 20. In the median case, roughly 20% of the sources get polluted by a given prefix hijack. Well, if you just add 1 or 2 of this ability for you to go indirect through an AS that's going to deliver your traffic, then you can eliminate almost all of those. And so that would be my example of where you can eliminate a bunch of problems that would otherwise be that you would have in the broader internet by allowing this at an incremental level. So that's the talk. I'm happy to take questions.
So, okay, while people are getting up to ask questions, please use the microphones. I will just ask a very quick question. Sure. So how does that relate to net neutrality? Is Google to buy the internet?
So we have, actually, it's an interesting story. So we had done, where this set of ideas came from for us was that we had tried to look at what a network architecture would look like if you tried to design a network, again, from scratch. If you tried to design a network where network neutrality was enforced by the network, so that it was impossible for ISPs to discriminate on the basis of the destination of traffic or the source of traffic. And you're like, oh, okay, how can they do that? Well, suppose it was the case that actually instead of having an IP packet that had a source and destination in it, would say, oh, this is a Google packet and this is to Tom, and Tom can pay a lot for his traffic and Google can pay a lot for his traffic, so great. Let's charge them a lot, or if they're not willing to pay, then we'll degrade the service. If instead we said that the packets didn't have addresses in them, or rather just had hops, then you'd be able to eliminate, or at least at an architectural level, say that you wouldn't have network neutrality. So this is in the direction of being able to say, well, now Comcast maybe can't discriminate against Google because it doesn't actually know where the traffic is going and where it's coming from.
The solution to one of the problems relied on convergence of global distributed consensus. So is the intent to be better than today, or is there a reason that this will be a completely safe assumption?
So the distributed systems community has made a lot of progress, which many of you are probably not aware of. But the model that we were operating under was that there would be a small number of organizations, so half a dozen, some number like that would be running the consensus algorithm to decide whether updates got adopted or not. So and what's true of these protocols is that they're fault tolerant. They can even be made Byzantine fault tolerant, which is to say, even if it's the case that you have an ISP that's trying to mess everything up, but everybody else will still be able to make progress in a reasonably efficient way. It's a message pass back and forth, or a few rounds of message passing back and forth to be able to agree on an update. And then you can batch them, so you're only doing them, say, every couple seconds or whatever. You would batch up the updates you've seen up to this point, and then send them out and apply them, and batch up the next set and then apply them.
Do we have additional questions? Okay, excellent. Then I would like to thank Tom again.
Leaving this on.